All right, well, welcome everybody. I'm Charles Polini. This is Lyle Axelaris, and we're going to give you a little presentation today on hygrothermal modeling and how that influences our building envelope design. So give me one quick second and we'll go ahead and get started here. Hopefully everybody can see my screen now. Cool. Yeah, we'll go ahead and get started. So again, we're talking about hygrothermal modeling, hygro, moisture, thermal, heat, and again, the transport of those materials in and through a wall assembly. So a quick introduction to us. I'm Charles Polini with Harrison Kornberg Architects in Houston, Texas. I'm also a BAC alum. Graduated from the Distance Masters of Architecture program in 2017. So Harrison Kornberg's about 30 people. We're a minority business entity. We consider ourselves a very diverse firm. My focus is on higher education and building envelope design primarily, but our firm also does K through 12, civic, aviation, and sports facilities as well. So, and then Lyle.
And I'm Lyle Axelaris. I'm an engineer and a building enclosure consultant with Design Alaska. We're a full-service AE firm based in Fairbanks, Alaska. We have many government clients with properties all over the great state of Alaska, and we also serve a lot of projects in the education and healthcare sectors. And we perform a lot of design build projects, so we've really come to have a great understanding of contractor means and methods, and that informs a lot of the critical building envelope designs that we do in such an extreme climate. It's really important to get this right. I'm also the instructor of BAC's building envelope course through the Sustainable Design Program.
Awesome. So quick little introduction about building envelopes and some history so that we can see how we got to where we are now. So for most of the history of our buildings, there are sort of two modalities depending on your climate. The first is the idea of just heat it up, using heat and warmth to drive moisture out of your walls. So the building envelope per se was really just a weather barrier to keep bulk water out, rain off your head. There's no sort of formal thermal insulation. We left our wall cavities open. Sometimes you'd see, tapestries hung on the walls to prevent draftiness in old castles. But that's about the extent of thermal control in most of our cold climate buildings historically. There's often a masonry fireplace that provides radiant heat to most rooms to sort of heat up the inside. And what this does is it negatively pressurizes the house and draws air through the wall assembly for that drying effect to keep moisture out. In hot weather climates, we see a slightly different modality there. We're looking at trying to air things out. You'll see, a lot of high ceilings and attics to allow hot air to rise out of the living zone. We've pushed our chimneys to the exterior so that heat radiates outward and not inward to the living spaces. And then you'll see a bunch of strategies to try and catch and amplify breezes and airflow through a building. Long, low roof lines with porches and overhangs to act as wings. This house on the slide now is an example of a dog trot, which is two separate living areas separated by an open breezeway. That air comes through the building and draws heat and moisture off of those two separate living spaces. You'll also see either basements or cellars or raised plinths acting as sort of a geothermal heat sink and capture some of that cooler ground temperatures to draw them in. You'll see that one example here is the Laura Plantation near New Orleans. With a they also, that raised plenum, that brickwork pier, is absorbing the groundwater as well and acts as sort of an evaporative cooler to help cool down the house. So moving into the 20th century, we start to see technology influencing our building envelopes. And for the first time, we're starting to think of the building envelope as a heat break. So in the 30s and 40s, we see two really big changes in our building envelopes. One of them is Dow Corning's invention and widespread distribution of fiberglass insulation. And then the other is the sort of the widespread use and development of central AC. So we start to see these two systems working together to change our indoor environment and to change the nature of that exterior envelope. So now that our walls are becoming true thermal barriers for the first time, now we start to see some of these moisture issues. Again, we're slowing down that airflow that's traditionally sort of dried out all of our walls pretty easily, something we haven't had to worry about before. And then we're also seeing the influence of some of these new products. Vinyl wallpaper acts as a vapor retarder. Latex paint starts to act as a vapor retarder in ways that oil-based paints didn't before. And so we're seeing some of these materials start to come in that are slowing down the drying process of our envelopes, which is starting to create some moisture issues that then need to be addressed. So that brings us sort of roughly to where we are now in sort of our modern sense of the idea of the exterior envelope, this idea of seal it tight and then ventilate right. So what we've come to sort of learn is that sealing air gaps in buildings, that's a good thing. Sealing moisture in buildings, that's bad. So we need to be able to, again, stop that flow of air, but still allow that flow of moisture. So modern building envelope strategies sort of focus on several, key points here. One's limiting thermal bridging, so using continuous insulation to really keep those highways for heat at bay. The next is to prevent air infiltration or exfiltration, keeping when we're heating air inside, keeping that hot air in. When we're cooling it down, not letting the hot air from outside to slip in through those walls. And then lastly, mitigate moisture buildup in the assembly. And then just a quick pitch, we're not going to touch on this too hard in this presentation, but just a reminder, good envelope design must be coupled with good ventilation strategies for your indoor air quality and manage humidity and moisture. So shout out to all you mechanical engineers out there, or shout out to call your friendly neighborhood mechanical engineer. To take a look at some of these components in a little bit more detail, there are several primary components of the building envelope. The weather barrier, the thermal barrier, and then the air control layer. Those layers don't always have to be in that order. The weather barrier does generally sit on the outside, but that air and thermal barrier sometimes will flip-flop depending on your climate or the way you have your wall designed. So first look here is at the weather barrier. This is the side that we present to the environment. So the sort of the governing ethos for weather barrier design is the 4 Ds: deflection, drainage, durability, and drying. So we're trying to deflect bulk moisture, keep rain off of the assembly, off of your wall, out of your wall as much as we can. And then secondly, drain any moisture that gets in off so that it doesn't just sit and soak into that assembly. The next is durability. We're protecting not just from physical damage like hail and flying objects, things that the wind picks up and throws at our walls, but also from things like UV radiation, long-term exposure, degradation. We're really trying, a lot of these other layers in our wall assembly are much more fragile, and we want to make sure that we're protecting those so they last as long as possible. And then lastly is drying. We want our assembly to be able to dry out for any moisture that gets in to be able to get back out, because as we all know, water always wins. You will always end up with some sort of water or moisture in your assembly, and we want to make sure that there's a way for that to get out. So the next layer is your thermal barrier. So what we're trying to do is slow the transfer of heat through the assembly. We're trying to keep, again, either keep the heat outside from getting in or keep the heat inside from transferring out. Remember, heat always flows from hotter to colder. So we're trying to tackle that issue. One of the big things that we've noticed or looked at as through the years, and are really addressing, you're seeing it more and more and more in the building codes, is this idea of continuous insulation and thermal bridging. So, looking at this sort of typical wall section over here, we see that our sort of primary wall assembly is, gypsum board, fiberglass insulation, plywood, and then a layer of exterior mineral wool and on the outside in terms of our thermal control layers. But if you look, heat will also transfer through the studs that break up that fiberglass insulation layer, and adding in a stud as to break that thermal insulation lowers the R value of that path by like 33% in this case, a full third. So we really want to limit the number of places that we're letting heat sort of get transfer through the wall in such a speedy manner. So just another note before I leave this, a reminder that insulation layers can be air or vapor permeable or impermeable. So always make sure you're looking and checking for that, because that'll influence our next thing, which is talking about air and vapor barriers. I think this can sometimes be a little bit of a confusing thing for architectural students and designers as we go through. So when we talk about air barriers, we're talking about limiting the movement of actual air through a building. It's keeping wind out and things of that age. So if you look at on the side here, I'm showing you can see an image of a blower door test. So the way we test for air leakage in an assembly is to tape off a door of the house, put a pretty large fan here that blows air into the interior, and then they fill they pump a little bit of theater fog into the house, and then go outside and look, or house or building, and then go look to see where that starts to leak out, and they can actually measure the amount of air leakage that you get through your assembly. This is what we're trying to prevent. We're trying to prevent this sort of indoor air, this conditioned air, from mixing with the outside unconditioned air in an uncontrollable manner. Just a little bit of sort of tidbit facts for you. It's funny, actually, this is the conditions outside my window right now. It's about 95 degrees out. It's about 95% relative humidity. That means that the air has about 60 BTUs of energy per pound of air, 4.2 BTUs per cubic foot of air. The indoor air, 70 degrees, 50% relative humidity, generally good design temperature, 1.9 BTUs per cubic foot of air. So if you run your bathroom fan for 10 minutes, at, just say an average 100 CFM bathroom fan, you run it for 10 minutes for a 10-minute shower, you're getting almost 1,400 BTUs of energy in through that has to be reconditioned because you're dumping that outside. So vapor barriers. Vapor barriers or vapor retarders are about limiting vapor osmosis. That's the molecular process of water vapor in the air, those little H2O molecules diffusing through a solid membrane. It's not about airflow. It's about that finite that minuscule molecular process. And those are graded class 1 through class 3 based class 1 through class 3, sorry, based on their perm rating, or how many molecules they actually let through over a set period amount of time here. So class 1 is essentially a vapor retarder, and then slowly work their way up. So also just a note, a reminder that all of the layers in your wall assembly have some vapor retarding properties to them. Even the ones that aren't necessarily designed that way. So we've already mentioned latex paint and interior vinyl wall coverings, but insulation slows down the movement of air, or slows down the movement of vapor. Your drywall slows down the movement of vapor a little bit. So we have to look at this as a holistic process. And
we're going to switch screens now, and I'm going to show you how we look at that as a holistic process by using technology. And so, Charles, if you can just let me know when you see my screen.
All good to go.
Okay, great, thank you. Okay, so now we're gonna leverage all that building science principles that Charles just shared with us, and use technology to see how it informs our building envelope design to meet the incredibly high performance standards that we demand of our buildings in the 21st century. And so the first means of kind of hygrothermal analysis that we use as an industry was the dew point method. And this, even though this was developed by ASHRAE, which is the Mechanical Engineers Society, basically, they now say don't use it, and they have said that for a while. They said this is it had historical importance, but it is way too simplified to use reliably as a design tool. And I'll demonstrate what some of the shortcomings of the dew point method in order for us to understand where the technology is nowadays in the 21st century. And so this is a code compliant, IECC compliant wall assembly for Boston, where it's a 2x4 framing with batt insulation, plywood, and then 2 inches of EPS insulation. And I'm going to specify that this is faced EPS insulation, which is the kind that you get in the box store. It has that polypropylene facing on it, where they stamp, the manufacturer stamps the brand name and some R value information on it. And we'll come back to that because that's a very important factor. But for now, we're talking about just thermal properties. This is the dew point method, where we take the inside temperature of 70 degrees. We take the average coldest temperature for the coldest month, January, which in Boston is 26.5. According to the latest ASHRAE Handbook of Fundamentals. And you chart out the thermal gradient from inside to outside. Temperature drops at each point in the wall cavity based on the insulation properties of each material. And the point of this, according to the dew point method, is to find where is the dew point in our wall assembly. And in this case, we assumed 60% relative humidity on the inside of the building. So the dew point's 51 degrees, and that falls somewhere in the fiberglass insulation layer. And so what that means is that the first surface of the first material that is to the left of the dew point, that's below the dew point temperature, that is the plane that we expect to see condensation forming. And so, and that is what we often see in cold climates and even mixed climates like Boston. But the traditional use of this approach was, okay, so the dew point occurs here in the fiberglass, so we need to put a vapor barrier somewhere to the right of the dew point temperature. We'll put it right here, just right behind our gypsum board, and then walk away. We're done. Building envelope design is done. We're not going to have moisture problems. But in reality, we have very different climate conditions throughout the year. The design temperature from ASHRAE, the design temperature on the heating season is 8.5 degrees, and the cooling season it's 90.6 degrees. And we see the location of the dew point temperature is in different places at different seasons. It's way outside of the plywood in the summer, and so we expect to see condensation on the outside surface of the plywood in the summer. Well, we didn't account for that in our building envelope design. And there's also hourly changes, day and night. It can be wildly fluctuating in some climates. And so this is really too simplistic of approach. It's only looking at a snapshot of one of the 8,760 hours that occurs every year. Even more importantly than that, though, the dew point method approach is really it's centered around the idea of vapor diffusion, and that being the main enemy, the main thing to protect against in a wall assembly. And we know that that's a small fraction of the moisture that accumulates or that flows through our wall assemblies is from diffusion. Much greater contribution, especially in cold climates, is this exfiltrating air, the vapor-laden air from the inside finding its way through the wall assemblies, through gaps and cracks, and every hole that's in that vapor barrier from screwing the gypsum board to the wall, that's a hole in our air barrier layer, and it's bringing that moist air into this cold wall cavity where it can find that plywood condensing surface. And then, of course, in Boston, you see it a lot. Certainly in Houston, you see a lot of that driving rain, that wind-blown rain going up against your building. And a lot of that's going to get through the gaps and the cracks and joints in your cladding system. Maybe some gets behind the windowsill flashing if there's not end dams and back dams and all these best practices. And then there's even thermal conditions that are ignored. There's nighttime cooling radiation, solar radiation. These have major effects of what the thermal conditions are of each of these building envelope layers. And then I think the greatest shortcoming is really that this dew point method approach was kind of taking a hard stance on moisture management and just drawing a line in the sand saying we are not going to let water get into our wall assembly. And it's a little bit of a stubborn approach of that it's possible to completely stop moisture migration, and it just isn't. We know, like Charles said, water wins. Water's going to get in from the outside through flashing failures, through time, through damage, through little holes that mice chew into things. And then moisture is going to get in from the inside, especially in cold climates, through little holes in the air barrier, and having that humid air flow through our wall assemblies and find a condensing surface. And so moisture management, hygrothermal dynamics, it is dynamic. It is a constantly changing thing. The temperature and the humidity is constantly changing. And it's a matter of balance. It's kind of a classic engineering situation where we have flow in, we have flow out, and there's a buffer, a storage capacity of certain building materials, the porous materials like concrete, masonry, wood studs, plywood, gypsum board to some extent. These can store some of that moisture, and they could safely store it, or they could unsafely store it. And so if the accumulation gets above that safe storage capacity, that's when we start having the problems of mold growth, structural rot, discoloration of finishes, corrosion of fasteners that leads to real life safety challenges with balconies falling off buildings, or railings falling off buildings, or heavy cladding falling off buildings. All of this needs to be accounted for. And so I just want to pause here and say, now that we've kind of discussed the moisture damage, this isn't all about indoor air quality or life safety. Even the most hawkish among us on energy stuff, which is great. We all need to be very aggressive in our energy efficiency, but we need to realize that if we are ignoring the moisture performance of the wall assembly, we're shooting ourselves in the foot on the thermal side, because wet insulation is bad insulation. And so this is 6 different insulation types, and all of them, as you increase the moisture content, all of them decrease their R value per inch, and some of them very dramatically. And so we're really trying to improve the thermal performance by improving the moisture performance of our wall assembly. And so now I'm going to show how we can move from that from that older dew point method approach into the modern hygrothermal modeling approach and see what we can learn from that. Now, Woofy is the hygrothermal modeling software that I use. That's the kind of um, the best program, the kind of industry standard program that's out there currently. It's a long German name, so I'm not even going to try to pronounce it. I'm just going to call it by its abbreviation, which is Woofy. Yeah, sorry, I lost control for a sec there. It's we're going to set it up similar to the dew point method example we gave. Okay, same wall assembly, the Boston IECC compliant assembly with that faced EPS insulation, and we graphically represent it here in the Woofy model, where the interior is on the right and the exterior is on the left. And what the model does is it's a finite element analysis. So it takes each, very, very small, a finite element of each, many of them in each building layer. The gypsum board, there's the vapor barrier, there's bad insulation, plywood, EPS insulation, and then our air cavity and metal siding. And it's going to look at the temperature at each of those conditions, at each of those elements, and see what happens to that temperature as it changes based on a climate file from the outside. So I'm going to start playing an animation of the results of this model, and I'll explain what's happening as it's going on. So here we see the outside temperature on the left is increasing every day, every hour throughout the day. When you see a little yellow sun here, that is actual solar radiation hitting the side of that cladding, which changes the thermal conditions and it's driving heat more and more into the wall assembly. And as a result of those changing conditions, and also as a result of the material properties, the relative humidity in each of these elements is changing. And you can see it's pretty dramatic, the change. Of course, this is sped up. This is very fast motion animation, but the conditions change in that relative humidity of all the building materials. And based on the material properties of the vapor permeance, of thermal conductivity, how those properties change with both temperature and relative humidity, it's calculating all of that for each element for every hour for this model that I ran for spanning 10 years. But the properties of each material will determine how the relative humidity in that material affects moisture content, which is this blue line. And so we see this blue line, the moisture content, it's changing just like the others, but a little slower because there's that storage effect. This kind of creates a lag or an inertia in the system. But we see specifically what's happening in this climate in this model is the plywood layer. It's actually OSB. We see water accumulating there, and it accumulates sometimes because there's a driving rain event from the outside. Well, you'll see a little peak like we just saw here, but it's also accumulating from that vapor-laden air from the inside that exfiltrates to the outside in the winter. That's what we're seeing, a little bit of that now. And you might be asking, why this is a very unsafe level of water content now. So what's happening? So we have a vapor barrier on the inside that's slowing the vapor diffusion into the wall, but it's also completely preventing vapor diffusion from leaving the wall. So it's not able to dry to the inside. It's also not able to dry to the outside because that polypropylene facing of the EPS insulation, like I was explaining before, that facing material is a vapor barrier. It's a class 1 vapor retarder, otherwise known as a vapor barrier. And so it slows down any migration of that moisture, that diffusion of moisture that's trying to get to the outside, to the air cavity, where it can be, released to the atmosphere. And since it can't move there, it's kind of just staying in the OSB. And so we get an overall net accumulation of moisture in our critical OSB layer. This is the classic double vapor barrier problem. We've had major problems with this in Fairbanks, Alaska. If there's a vapor barrier on the inside of your wall, you cannot be using a low permeance insulation like Charles was saying, because that is acting as a vapor retarder, sometimes even a vapor barrier. And in this case, it's the facing on the insulation that is trapping that moisture in. So let's fix this. First thing we're going to do is we're going to replace that insulation with a high permeance insulation, mineral wool insulation. It's very high perm or vapor open, you might say. And I'll start playing the animation and we'll see what happens. We have the same R value because mineral wool is almost exactly the same R value as EPS insulation, but it's breathable, so to speak. It's allowing that vapor to escape to the outside. Now we still see those peaks, those spikes that we just saw from the weather climate file. That's some driving rain. And we, according to ASHRAE standard 160, which is the standard for hygrothermal modeling, we apply 1% of the driving rain to the surface of the water resistive barrier. So whenever there's wind and rain in the climate file, it takes 1% of that amount and it applies it to, basically a 1/4 inch layer in this insulation. Now, mineral wool is heavier than EPS insulation, so that's why these spikes seem higher. They're not. It's the same water that's being added. It's just a higher water content because the mineral wool density is higher. But each time we see that driving rain, it does affect a little bit the moisture content in the plywood because it's a colder surface on the other side. Now it might affect it affects all the thermal and the hygrothermal dynamics. And so you'll see a little bit of buildup of water in the plywood when there's that driving rain, but then it comes back down because that plywood, see it's building up now, and pretty soon we'll see it come back down because once the conditions are right on the outside, the moisture will move to the left. And that's what these arrows up here, they're pointing to the left a lot because that's the direction that the water is flowing. And so if I just skip forward in time a little bit, do a little time warp, we see even 3 or 4 years out, however far we are, there is still a kind of balanced, pretty safe level of water content in that plywood. It's not up to the 50% range like we saw in the other model. And so if we just create a graph, the OSB moisture content in the first model, the faced EPS insulation, what we see is that water was accumulating in the OSB, and it was kind of the seasonal summer and fall, really driven more by the exterior high humidity and the hot, humid summers that you get in Boston. Accumulating pretty fast in the OSB, then it kind of stabilizes during the winter and spring, and then it goes up again in the summer. But it never comes back down to a safe level. Sorry, turn my pointer back on. It never really comes back down to a safe level. So there's a continuous trend towards increasing moisture content. And that's because the wall can't dry to the inside and it can't really dry to the outside. It's that double vapor barrier problem. In comparison, when we switched it with mineral wool insulation, we see lower levels of moisture content in the OSB. And it is in the fairly safe range. We'll take a look at that in a second. And their peaks are, while you see the repetition, the pattern every year, the peaks are more driven by individual driving rain events because that loads the wall with a little bit of moisture and then it quickly dries because it's allowed to dry to the outside. And then there's again a little bit of a spike from driving rain or maybe a little bit of wintertime condensation, just some thermal condensation, but then it dries. And so that's an interesting study of what insulation to use. But then we really want it to be high performance. So we say, well, what do we even need that interior vapor barrier? So I ran a third model because I know what the answer is on the assemblies that I design in Fairbanks, and it's all based on what our insulation ratio is, how much outside insulation is there versus insulation in the cavity. But for Boston, I'm not as familiar with. So I ran a third model where there's no interior vapor barrier. We have the same air tightness, same amount of air leakage, but we still have a good air barrier on the outside of the building. And I get this green line. And in general, it looks like for the most part, there's less moisture content in the plywood most of the time, but then occasionally it's higher. And it's higher in the spring, the winter and spring. So you're seeing a little more wintertime condensation because you don't have that interior vapor barrier that's slowing down that diffusion process. But much lower water content in the summer months, July, August, September, when you have that vapor drive from the outside. And those are really the critical months that we want to keep our materials dry, because that's when the temperature is warm enough for mold growth to really take off. And so in order for mold growth to occur, we need depending on the material, but about 80 to 85% relative humidity and at least 40 degrees Fahrenheit. So that winter, that extra moisture content in the winter may not really be a problem as long as it doesn't get up to 15 or 19%, where it does cause some structural degradation. But the corrosion and the mold growth, that really needs the temperature. And so we're going to really look at that now. Is that green line a better assembly from a mold growth perspective? So we're gonna get even nerdier now. We're going to go to a bio-hygrothermal model, and this is done by WUFI. This is taking the moisture content and the temperature conditions in a specific element that we select in the WUFI model, and it runs it through a second model that analyzes mold growth, and it's based on lots of laboratory studies of what the conditions are needed for mold growth. And so this first line, the red line, was our EPS wall, the first one, the double vapor barrier wall, and we see it just climbed and went way off the charts, kind of stabilizes up to almost a 5.0 mold growth index. The mold growth index is created in by ASHRAE. It's ASHRAE standard 160. And they basically say 3.0 is like the compliance threshold. That's the most mold that they think is acceptable in a wall assembly. And that amounts to less than 10% visible coverage of mold. And if you look at the wall under a microscope, you would see anywhere up to 50% mold growth. And so I think that's kind of high personally, but clearly the red wall is unacceptable. The blue line is the mineral wool insulation, but there's still a vapor barrier on the inside. And we see that it is technically a compliant wall assembly. It kind of levels out just below that 3.0. But green is when you have no interior vapor barrier. And that is a very marked difference in the mold performance. And again, it's because the moisture content was so much lower in those critical, hot summer and fall months. And so even though we look at the water content, they look a little kind of similar, but when you look at the mold growth index, much different. And really, so what we learn in this case study is that when we're talking about vapor diffusion, when we talk about placement of vapor barriers and the resistive vapor, the permeating of different materials, more important than wetting is the drying. We need to be considering at least one path of very high permeance vapor open, so there's an escape pathway for any moisture that accumulates in our building envelope assemblies. And so drying is more important than wetting. And when we saw that double vapor barrier from the polypropylene facing on the EPS insulation and our polyethylene sheathing on the inside, moisture couldn't really go anywhere. It's just trapped. Whereas when we kept it vapor open on both sides, we saw sometimes it's dry on the inside, sometimes it's dry on the outside. Overall, it stays dry. And then the next case study we're going to look at is about climate. Of course, we're all thinking about climate now and about future proofing our buildings. But first, we need to know, where are we designing our buildings? Some of us work for national firms where we design from climate zone 2 to climate zone 5 or 6. And climate really does matter. Not only do we see huge difference in heating degree days and cooling degree days, but the extremes, like Charles was saying, 95 degrees and 94% humidity. I can't even imagine that. That's like unfathomable to me. Whereas 17 below is our average low. We used to get down to 60 below. Now it's more like 40 below is kind of as cold as you'll see in Fairbanks, but still extreme cold. And I like this graphic just to kind of remind us how far away Fairbanks, where I work, is from Houston, where Charles works. And it takes 66 hours of nonstop driving to get from point A to point B, or 8.5 hours of flying, which is a long flight. But it'll only take one summer, one winter to completely ruin a building if you design it for Houston and build it in Fairbanks, or vice versa. And so to show that, to kind of test that theory out, we're going to look at a couple of prototypical wall assemblies. The Fairbanks wall assembly is gypsum with that interior polyethylene vapor barrier, then 2x6 wood studs and fiberglass insulation. We have plywood sheathing and a vapor open, vapor permeable, air and water resistant barrier like a building wrap, and then 3 inches of mineral wool insulation, which again is vapor permeable, and then a rain screen with air gap and metal panels. The Houston wall assembly that we'll look at is going to be very similar. It's just metal studs and gypsum instead of plywood. But the key thing is that there's no interior vapor barrier, and instead of 3 inches of mineral wool, we use 2 inches of mineral wool because that's appropriate for Houston. And I will just say 3 inches of exterior mineral wool with R21 bat in Fairbanks is right on the line. It just meets ASHRAE 90.1. Typically, we'll do a lot more exterior insulation. And so I'm not going to go through the animations. We're just going to look at the results. So our OSB moisture content for the Fairbanks wall, built in Fairbanks, we have seasonal wetting during the winter, and then it dries quickly each summer because Fairbanks has beautiful, 21 hours of sunshine on the solstice, and every day is sunny and it's dry. It's just gorgeous. You guys should all come. But that is great for our wall assemblies because as long as the winter is and as much moisture as we can build up on that plywood, it just dries really quickly to the outside each summer. And so this stays constant, even though it fluctuates, it stays below the safe storage capacity of the OSB, and we don't get any mold growth. But in comparison, if we use the Fairbanks wall assembly and we build it in Houston, we see a very different story. The August, July, or really August and September during the hurricane season, there's a high exterior humidity, driving rain, lots of moisture loading from the exterior. And the Fairbanks wall assembly isn't designed for that because it has that interior vapor barrier. And so that wall, all that humidity loading into the wall assembly, it kind of backs up when it hits that vapor barrier. And we start seeing the storage capacity at OSB getting overloaded, and there's a sudden spike. And then, around October, November, the exterior dries out a little bit, and so now the wall assembly can dry to the outside and the moisture content gets low. But during those critical warm months, there's so much moisture in that OSB that it is very conducive to mold growth. So we get a mold index of 3.7, which is unacceptable. So now let's look at the Houston. If we build the Houston wall assembly, remember it has no vapor barrier, very low, very high vapor vapor resistivity in both directions, right? High perm ratings. And so even though there's such a high moisture load from the outside, it kind of just flows right through the wall assembly because the interior conditions are relatively very dry because of air conditioning. Air conditioning has that dehumidifying effect. And so it's 95% relative humidity outside. It's somewhere in the 40 to 60% range inside. And so that moisture doesn't ever really have any time to build up beyond safe levels in the OSB. So as a result, we have no mold growth, 0.0 mold index. But if you put the Houston wall in Fairbanks, we have major problems. And the biggest, so we see all winter long, we get steep spikes, very high moisture content. Now we see the drying effect each year, and it dries back down to a very safe level, and it dries in those gorgeous summer months in Fairbanks. But it's just too high of a moisture content for that drying process to start with, and so it doesn't get down to a safe level by the time the temperature kicks in, which is in May, but really more June, July, August. And so there's enough warm months where there's very high moisture content, and we get a mold index of 5.0. And really the main driver for this, I think people's intuition might be, well, okay, yeah, that's why you need a vapor barrier on the inside, because it's preventing that vapor diffusion into the wall. And that's true, but really, again, it's our air barrier that's doing most of that, preventing the air leakage into the wall assembly. The reason why we see so much condensation here on the Houston wall is because they use 2-inch mineral wool insulation instead of the 3 to 6 inches of mineral wool insulation that we typically use in Fairbanks. And what that means is that plywood layer is colder than the dew point temperature for many more hours each winter. And so there's more chances for condensation to start forming in that plywood layer. And so we really, in extreme cold climates, we manage condensation a lot by just our insulation ratios. If you could have all the insulation on the outside of your plywood, you won't ever have condensation because your plywood will be dry and warm and safe. And so, you know, in summary of this, the climate does matter because we have very different conditions, very different sources of moisture dynamics, storage capacity, and drying potential. In Fairbanks, most of our moisture is coming from the inside of the building due to that exfiltrating air. And on the outside, we have minimal rain. It's almost a desert, low humidity, and lots of drying potential. And we have extreme cold, so that's driving the thermal and the air pressure gradient from inside to outside. But in Houston, most of their moisture source is coming from the outside. They have that driving rain, high humidity, and extreme heat, and that's driving everything from outside to inside of the building. But because they designed their walls correctly, they can have it dry. They have drying potential to the inside when they're running their air conditioning. And then sometimes the climate's actually dry enough on the outside to have the wall dry to the outside. But they make use of both directions to maximize their drying potential. And so now, you know, implementing this practically in our practices in the design profession, we need to take what we learned from WUFI and obviously have it impact our, inform our design of wall assemblies and our roof assemblies and our floor assemblies. But we need to maintain those principles, the building science principles that Charles was discussing. We need to maintain that throughout the entire building envelope. And so at every penetration, every transition, every detail, we need to make sure we have thermal barrier continuity. And especially in cold climates, we need to make sure that we wrap our parapet or our rakes, if it's a exterior insulated roof, which we actually do sometimes in Fairbanks. We need to make sure we have thermal barrier, our insulation wrapping all the way around it to make sure we avoid those thermal bridges. We need to maintain air barrier continuity. Is very, very important to have good air barrier details to make sure we're not getting any air leakage into these, especially these cold kind of peninsula cavities that we are formed in a parapet stud, for example. And our water barrier continuity always needs to be continuous. In this case, we wrap it around the outside because we're always about protecting the framing and the plywood or gypsum board sheathing. And finally, we need to look at our balanced vapor profile. Are we providing a means for the wall assembly or for this particular detail to dry out should there ever be any accumulation? And so it could dry to the outside, or we could dry to both the inside and the outside, depending on our design. And now this is a detail that Charles is developing, and he's going to explain real-world application of these principles.
Yeah, so this is a project that's actually under construction now. This is a plan detail of a tilt-up concrete building here in Houston. And one of the interesting things as you look at it, we still do have that thermal continuity layer. The insulation wrapping the inside. We have that air barrier layer that we've installed on the inside of the concrete in this particular case. And then we also have that the concrete itself is acting as that water barrier layer on the exterior. This assembly is interesting, again, just as a little bit different than that sort of standard Houston wall that we were looking at. You can see we still have all those layers. They're still all essentially in the right order, you might say. But you can see that water barrier and that air barrier are in many cases very far separated. And then we also need to make sure that we're looking at that vapor profile and how that vapor is getting out, letting the concrete that is prone to absorbing moisture can in fact dry to the outside, and then making sure that any moisture that does sort of mitigate or transmit through that material can dry to the inside with that AC moving. So again, just sort of looking at all of your details and making sure that we are keeping those three major continuities rolling and truly continuous, regardless of what your structure is or regardless of sort of what your details and conditions are.
And so if anyone's interested in learning more about hygrothermal modeling, the Oak Ridge National Laboratory has some good resources, some kind of primers on modeling. They even have a free version of WUFI that's very limited, but still a good introduction to getting used to, playing around with the models and learning from it. Just a quick caveat, or a warning, I will say, with any kind of model or complex calculations, there's a saying, garbage in equals garbage out. And, basically you need to make sure that you're putting the right information in so that you can trust your results. Because if you start changing things and you don't fully understand what the impacts might be, you might be giving it poor information, getting poor results as a result of that. And so, but please email either me or Charles with any questions you may have, and we look forward to answering any questions you may have at this time too.
So I think there's a question from Marjorie in the chat here about how we design for such a fluctuating climate like the Northeast. So I'll let Lyle go first.
Well, this is Fairbanks, Alaska, it's like we've been doing really tight air barriers for decades, since like the oil crisis in the 70s. And it's simple for us, and it's all kind of one directional from inside to outside. The Northeast, these mixed climates, it is very challenging because you have the vapor drives going in different directions. I think the two things, the key thing is making sure that you're focusing on drying potential and just kind of going with the flow, and knowing that there is going to be some moisture that gets into your wall assembly, making sure that there's a clear drying path, at least in one direction, if not in both directions. But I would also say kind of the second point is that it's a little bit tongue in cheek, but the idea of the perfect wall, the Building Science Corporation talks about, a lot of people have since written about it. But it works. It really does work in every single climate. If you have all of your insulation on the outside of your structure, and that structure is protected by a continuous air and water resistive barrier between the insulation and your structural sheathing, then your condensation, no matter whether it's coming from the inside or the outside, you're always going to get that condensation happening out in your insulation layer, and that water is drained and weeped away from your walls where it doesn't do any damage. And so it's like, who cares if there's a little bit of water that happens in your insulation? It will dry out and it'll still perform well, but your structure is always going to be warm and cozy and safe and above the dew point temperature. And so I know that that's not as common in the Northeast, but in Fairbanks we do it a lot, and I know some hot, humid climates you're starting to see more and more where it's just exterior insulation only. And I'd even rather sacrifice a little bit of R value than trying to do the split insulation approach, because you can really run into danger if you're causing condensation to happen in the middle of your assembly.
Yeah, I would say
helps.
Yeah, and I'll just add, we've done, our firm is doing a lot of projects, not quite all the way to Boston yet, fingers crossed. But we're working in Dallas. We're looking at a lot of, a fair number of consistent days of snow and cold, and I can say a couple of projects we've gone up there, we've done exactly what Lyle says. We've started to we've pushed the majority, if not all, of our insulation exterior, and just made sure that exterior insulation is mineral wool or some type that has a strong drying potential, push that outside that air and moisture barrier, and then being just incredibly protective of that air barrier layer, cutting down on the number of penetrations through it, making sure we're using air barriers that are self-sealing, and just, again, like I said, being incredibly protective. We're using a lot of things like Smart CI or Armatherm, those thermally broken fiberglass clips to hold up our insulation. And one of the things that we're seeing is you put down the air barrier first, you take that continuous thermally broken clip, you can apply some sealant to the back side of it so that when you poke your screw holes through, they're all protected as well. That's just one of those belt and suspenders kind of things that we're doing on a lot of those projects to really keep that bulk water out, protect from that moisture, and really focus on draining and draining out and drying both ways.
Yeah, that's a great point. I think just the last thing I'd say with that too is that, on the commissioning side, building envelope commissioning, or at least inspection, you might not need a full-blown commissioning program, but especially if you're in a region where some of these building science principles and some of the details, the high performance details might be new in the construction community, then you need to make sure there's an education component and there needs to be an inspection component to make sure that, something can look great on paper. You need to make sure it also looks great in the field, especially if they're new techniques that the kind of local construction community isn't familiar with, because the devil really is in the details. We know 90% of moisture problems occur in 1% of the location, or at least that's the saying. I believe it. So we need to make sure that we're giving them good information, our details, and that we're kind of following through with that quality assurance in the field.
Well, thanks everybody. We really appreciate you guys sitting in, and this was a great experience. So thanks very much. I hope you all learned a lot.